Okay, hi everyone. I want to talk about the integral test. So we've seen that um, that the convergence of the sum of 1 over n to the p, right? Sort of the p series we talked about. We see that this agrees with or behaves like, maybe I should say, the integral from 1 to infinity of 1 over x to the p dx. I think I said this in the p-test video, but mathematicians like to use x for a continuous variable. It could be any real number like √2, pi, whatever, and n for a whole number variable where you're counting like 1, 2, 3, 4. So that's one of the reason we use n. We use n in the series, and we use x in the integral. But we see that these behave the same, that if one converges, if and only if the other one converges. And we know how to test if the integral converges. We just do the improper integral. And that's how we showed that how the p series behave, right? We developed the p-test. What I want to say is that this technique generalizes. We can actually do this for any sort of function. So this is what the integral test says. The integral test says that so we generalize the kind of argument we gave here. And it says that if we have some sequence, some series that we're trying to sum up, and each term of it is the sequence of terms. So we say let a sub n equal f of n. So just in your mind, you should think, a n equals 1 over n, 1 over a n equals 1 over n squared. A n could equal, sine n, just anything that we sort of think of it just being like the function is 1 over x, here the f of x would be 1 over x. This is the way it's presented in the book, and it might look a little abstract, but it's just a way of saying, distinguishing between a function and a sequence, right? Where sine x is, for example, defined for every value of x, not just whole number values, but when we think about the sequence, we just want to consider the sequence, the values at whole numbers. So we would say sine n. So we would say this. So, and then I'll give you these conditions, and I'll explain why these are really important. So if we want f of x to go to 0. So we want, if this limit is 0, the limit is f of x as x goes to infinity to 0, and b, f of x is decreasing. So it's always going down. Then if that's true, it's sort of always decreasing everywhere. Then here's what the integral test says. The sum from, again, it doesn't have to start 1 to infinity, but we'll just write 1 to infinity here. The sum of a n, that infinite series, behaves like the integral from 1 to infinity of f of x dx. And by behaves, I mean it converges or diverges. Either they both converge or they both diverge. So both converge or both diverge. Okay. Let's talk about, why this is true. It's certainly true for the p-test, right? We know, so for the example of, over here, if f of x is 1 over x to the p, and then a sub n is 1 over n to the p, we get back the p-test, right? But I want to think about, this actually works for like broader classes of function than just the 1 over x to the p function. So let's just think about, why this works maybe, because we gave arguments for the p-test, why the p-test works. But let's look at, so by the way, this is what's called the integral test right here. That's the integral test. Let's draw a picture just to sort of see what we'd be thinking about here. So, right, we've seen a picture like this we saw for the p-test also, right? So here's my axes, and here's my function, and my function is decreasing. This is the f of x. It says we need it to decrease and go to 0. So it's just something that's going to look like this, right? It's going to be decreasing always, and it's going to be asymptotically heading to 0. I think it's actually important. I didn't really say this, but f of x is positive. We're going to talk about what happens when you have negative numbers in your series at some point. I probably should have said this in here, but for now, we're only talking about positive series where you're just always adding something. You're never subtracting anything. And then if we take the integer, x values, so now I'm drawing those on the x-axis, and then we take those points above those points on the function, right? Those heights are sort of like this function was y equals f of x. And the heights are like, this is like the height of this is a1, that's a2, that's a3, and etc., right? And the reason why we might believe this is the exact same picture we had for like when we did this for 1 over n or 1 over n squared, that you can sort of draw boxes. You can either draw, these boxes to show that the sum, so basically this, if it's like this is actually the sum from 1 to infinity of a sub n, right? These boxes represent that, as we saw with 1 over n. They're all width, each of these orange rectangles is width 1, and then its height a sub n. So this shows that the integral from 1 to infinity, I'll try to do this in colors. So we have the integral from 1 to infinity of f of x dx is actually less than the sum from n equals 1 to infinity of a sub n. But also, if we drew, when we did this, we did it slightly differently when we looked at the 1 over n squared example. We actually drew these rectangles, these green rectangles I'm now drawing on the picture, sort of like a right Riemann sum, and so on. And that was actually the sum from 2 to infinity. So that's actually, I want to say it this way. This is actually, you know what, let me do this. Let me move this over a little bit. I'm trying to claim that the series behaves like the improper integral, right? So on the other hand, this equals it equals a1 plus the sum from 2 to infinity of a sub n. But this last sum I just wrote here is actually less than the integral, because now that's the area of the green rectangles. So we can say this whole thing is less than a1 plus the integral from 1 to infinity of f of x dx. Right, so what I'm basically saying is that we've actually sandwiched our infinite series in between two improper integrals. And it's really the same improper integral, just one has an a1 and one doesn't. And so if both of these converge, if this converges, say this converges, and this converges, then we have something sandwiched between, so this also converges. But on the other hand, if they both diverge, if the improper integral diverges, so on the other hand, if it was, if this diverges, and this this diverges, they behave the same, right? It's the same improper integral, then that would imply that this diverges. And that's really the integral test right there. That's why it's true. It's because we can sort of always sandwich our series in between the improper integral and the improper integral plus something. And therefore the series behaves the same as the integral. You can also see why the conditions about the function decreasing are important. The conditions about decreasing going to 0 are important. So let me just draw this picture again. Well, let me draw another picture actually. So if the red, maybe I'll just say about this picture first. If the red wasn't always the red function, I've got the graph, right? The graph of the function right here. If this wasn't always decreasing, if this wasn't always going down, we could actually break this picture and break the inequalities below. We could break the argument. So for example, maybe I'll just do this in pink or something. If this, so now I'm drawing the red, I'm drawing over the red again, but if it was going down, but then all of a sudden it went up, right? And it's still going down there, but then it goes up and it's still going through the same points. That was not very good, but you get the idea. I can sort of be always adding extra area, and this would actually make this inequality right here with that would not necessarily be true anymore. It could be that the area under the curve is greater if it was now the pink curve, because now I'm sort of adding all this extra area here that could be sort of make up for the piece of the orange rectangle that's sticking up above the red curve. And so, yeah, we really need that. Actually, we really need that it's always going down. And I could do something, I could do a vice versa where or it could be like always, just use even another color. What colors do I have? This picture is getting very busy, sorry, but you could sort of redraw it again if you want. It could also do a thing where it's going way down, and basically you could break the other inequality also, right? I could have something that's going like this and it's going up and down, but it's still going through the same points. And then that could break this inequality and make that no longer true, that somehow the area under the curve would be less than the area in the green rectangles. And so you could actually see something like that where, you could come up with something where the areas do not, or that they don't match up. The integral might converge, but the series would diverge, or vice versa. So I could provide examples, but it would just get even a little more hairy. So let me not. So, but this gives some idea of why the integral test is true. Let me just do one example, just to show you how this works in practice. It's an example I particularly like. I'm actually going to start at 2, which you'll see why in a second. N natural log n, so n times the natural log of n. I can't start at 1 because natural log of 1 is 0, and I'd be dividing by 0. So this is 1 over 2 ln 2 plus 1 over 3 ln 3 plus 1 over 4 ln 4, and so on. One reason I like this example is that it actually fits in between these two tipping points. So like, we know that this series, the harmonic series, diverges, right? This diverges. We know that the sum, but as soon as we make the exponent bigger than 1, which is kind of crazy, but we know this series, actually I'll start these all at 2 just so they agree. We know this series converges because it's the p-test with now the exponent's bigger than 1. And I actually claim, though, that, so there's this tipping point at 1. There's this tipping point when the exponent is 1, where you have the p-test says that all of a sudden, if you're increasing the exponent, the series is diverging. And then if you make the exponent a tiny bit bigger, it converges and it's a tipping point. This example that I'm giving actually, though, lives in between. So it's not obvious whether or not this converges or diverges, because it's smaller than something that diverges and it's bigger than something that converges. And we know this is true because ln grows so slowly. This grows so slowly. It's still positive, so that makes the bottom here bigger than the bottom of 1 over n, or the bottom with the bottom of n. N natural log of n is bigger than n. But on the other hand, it's less than, because ln grows so slowly, it's actually less than any other power of n. So this actually fits in the middle. And so this is not something we can evaluate, as we'll see with comparisons. We can't just compare it to one of these p-series. It's actually right in that gray zone where we don't know what's happening. So in fact, we have to use integral tests. So apply the integral test to this. And so the function is clearly just 1 over x ln x. If we just turn the x's to n's, right? So a sub n is f of n in this case. And is, so we need to check these two conditions. It does the limit as x goes to infinity of 1 over x ln x equals 0. And the answer is yes, because the bottom's getting bigger and bigger. The denominator is going to infinity. So the fraction goes to 0. And is it decreasing? Does it always get smaller as you increase x? And you could give a similar argument here that, I mean, you could give an argument, a pretty easy argument that, yeah, like x increasing, natural log of x is increasing. So the product's increasing, so 1 over it is getting smaller. If the bottom's getting bigger, then 1 over it's getting smaller. But I do want to show you sort of a more general argument. We know a function is decreasing if its derivative is negative. Is decreasing if, right, because the derivative is the rate of change. And so that's true if and only if f prime of x is less than 0. So if we actually look at f prime, right, we might, this is a nice way to check. So if this is 1 over x ln x, I'm going to rewrite it as x ln x to the minus 1 power. So that means f prime of x, if we use the chain rule, we get minus x ln x to the minus 2 times the derivative of x ln x. But that's a product rule, so you get, and I think you can check if you do this, you get this when you differentiate x times ln x, because you get x times 1 over x, first times derivative of the second, plus 1, the derivative first, times the second ln x. So you get, yeah, 1 plus ln x. And so that is, if I rewrite this as a minus sign, 1 plus ln x over x ln x squared. And on the one hand, the bottom is clearly positive, right? We're squaring something, so the bottom is positive. On the other hand, if ln x is positive for x greater than 0, for x greater than 1, right? So this is certainly, this is positive for x greater than 1, and that's what all we care about here. And so this whole thing is we have a minus sign. So we get a negative times a positive divided by a positive, so that's less than 0. And so that checks out also. So that's one way to check if a function is decreasing always. And so it's nice, it fits the picture. It's not going to do this thing where it, like, we have these little bumps that show up or it's going up or down. It's just always going, the function's always going down. And so, well, then we need to actually figure out the integral, the improper integral, because we know the integral test applies. So if we actually integrate this, well, let's actually, before I even do that, let's just think about the indefinite integral, right? There's a nice u substitution here. So this integral actually equals the integral of 1 over u du, because the 1 over x dx is sort of, the 1 over x dx is right there. So this whole thing, that all can become du, and then we have a 1 over u, 1 over ln x. So then that is ln of u. And the actual integral here is ln of x, log x plus c, I guess there's a plus c, since it's the indefinite integral. But that means that the improper integral is really, so it's the limit as b goes to infinity, integral from 1 to b, 1 over x ln x dx. But we just figured out that is the limit. Oh, you know what? I actually want the integral from 2 to infinity because I don't want to take ln of 1. If I try to plug in 1 here, it's bad because that's negative infinity. So that's actually one reason we also started at 2. This right here shouldn't be a 1, it should be a 2. So this should be a 2. The bottom bound of the integral. Okay, so that's the limit as b goes to infinity of ln of x from 2 to b, which is ln of, oops, I forgot my limit. Almost done with this. So that's the limit. B goes to infinity of ln of b minus ln of 2. And it's funny. So log of b, I mean, as b goes to infinity, log b goes to infinity, just very slowly. But that means the thing you're plugging inside the log function is going to infinity. So that means log b goes to infinity, but just really, really slowly. So that's infinity. It's just, it diverges really slowly, but it does go to infinity. So this integral diverges. And thus, by the integral test, the infinite series also diverges, which was not at all obvious before we did this analysis. So there's your answer. Okay, so that's how the integral test works. All right.